Well, I think you will all enjoy the talk. So the floor is yours, Anastasia, please.
Okay. Good morning. It's my pleasure to give a talk today. And I'll just say a few words about my background as well. I was trained as a soil scientist, soil geographer, working with maps and classification of soils and remote sensing methods to assess the types of soils, different spots of the ground. And later on, I started doing ecological modeling, focusing on the nitrogen and phosphorus fluxes in the rivers and their traffic to the estuaries and the processes of algae blooms in the estuaries. This topic was very big in the 80s, in the 70s, and the 80s. Later on, I switched to modeling of population growth and especially focusing on cities. And now I am working with cities, but at different scales. I look at cities as a part of the biosphere, so the global scale. I also look at cities at the local scale, the country scale, also the regional scale, and sometimes, quite rarely, at the very local scale, as areas within the city. So you could see the quote from Aristotle here, that it's evident that polis, the city, exists by natural processes, and it's natural for man to live in the city. And in my view, it really reflects the nature of this problem, of the problem of organization, that the more people are on the planet, that they all tend to concentrate in cities, and also that city becomes a part of the nature or part of the biosphere and starts interacting with global cycles of matter and energy, but also at their local ones. When I'm studying cities, of course I'm interested in the number of people living in the city, but mostly in the area that is occupied by a city. Because from the biospheric research perspective, that's the most important part. The area of land is taken up by some entity that is not a natural ecosystem. So there are just some general facts here that cities, at the moment they occupy, at the moment they are home to 70% of people, of the global population, but they also emit 80% of all anthropogenic fossil fuel emissions. They are, however, taking only up to 2% of the total land. Still, this entity is very important when you look at the functioning of the biosphere machine, for example. So there are many different definitions of city, and especially sustainable city. One of the definitions is that city is some ecological system, and its sheer more dispersed settlement patterns dealing with many problems associated with them. This definition gives us understanding that cities should be more dispersed, so it should take more land. Yeah? I'll come back to it. Oh, by the way, if you have any question, you can interrupt me and ask right away. Yeah? It's important to understand when you study a certain city or certain problem associated with urban, that sustainable in relation to what? Is it, we are looking at sustainability in relation perhaps to flooding, yeah, or to food supply, industries, transportation, water waste. Usually it's like a set of things that we are looking at. but sometimes one can just focus on one or two and use them as some kind of indicators. Okay, and of course the rate of city growth is very important when we study city. How fast city grows, how fast the population grows, of course, but also how fast the area is expanding, or if the area is actually staying the same or expanding very little, but then the density grows drastically. When I look at cities from the global perspective, I use Vernadsky method. Vernadsky was a very famous Russian scientist. He lived in the 1920s and gave a set of lectures in Sorbonne. He actually came up with, or was the father of the concept of the biosphere, and he also is considered to be one of the founders of biogeochemistry science. So he uses this general empirical generalization method, which is scientific induction method that we usually use in natural research. From Vernadsky's perspective, that city is a new compartment of the biosphere. And also, as I said before, organization is a global ecological process. As the title of my talk suggests, I will talk about statistical methods of assessing cities' sustainability, but I will also focus on thermodynamic methods and on general biogeochemical concepts. Well, energy exchange is also part of the biogeochemistry, but I decided to separate matter exchange and energy exchange. I'll tell you why a bit later. So, city is an open thermodynamic system, and it maintains its structure through the conversion of energy. When you consider city as a component of the biosphere from a thermodynamic perspective, then you need to see that you need to look not just at the city, but what is surrounding it. So you consider city as some kind of super system with this environment, because that's where immediate exchange of matter and energy is happening. I will talk about exergy. It's a concept in thermodynamics, and the definition of exergy is how far is the system from thermodynamic equilibrium. And it's the highest when the system is far from thermodynamic equilibrium. So basically that system city is not in thermodynamic equilibrium with its surrounding. And when the system is with thermodynamic equilibrium with its surrounding, that means it doesn't exist anymore. It's there. That's the concept. So the further it is from thermodynamic equilibrium with its environment, the more sustainable it is, the more complex is the inner structure, and the more efficient is its function as a system. The main reference in thermodynamic approach is the book by Svirejeva-Hopkins, published in 2004, called Towards a Thermodynamic Theory for Ecological Systems. So we're all familiar with the entropy term. So entropy is opposite to exergy. So basically, when the city is producing a lot of entropy, it means that it's not functioning sustainably, that there are a lot of problems there with matter fluxes and also with energy fluxes. And that city, that particular city is actually very likely to deteriorate and to come up to the, and to move to a different state and become close with, to become in thermodynamic equilibrium with its surrounding. And then so entropy measures information that is needed to describe the system. When the information is available, for example, there is a lot of information in different biomes, but also in genes. It represents negative entropy. But the concept of negative entropy doesn't exist, so we use exergy. Conservation is important since when ecosystem is lost, huge amount of entropy is produced, since all the stored information is lost. All ecological processes are irreversible, and that's the main difference when you introduce thermodynamics of the living system as opposite to thermodynamics of the physical system in a classical sense. So when there is a lot of pollution, there is a loss of exergy. As a fact, there's a lot of entropy on production. Higher exergy levels, they mean higher buffer capacity. So exergy expresses both biomass and information. Information level can increase infinitely. This is all these concepts are used in regards to compartments of the biosphere, natural compartments, ecosystems, or biomes. But as we see later, it could be also used, implemented to study a city as a compartment of the biosphere. So anthropogenic pressure, and there's no natural ecosystem, so to speak. In highly industrialized countries, for example, it's really huge as compared to 100 or 150 years ago. We can maintain some kind of stability of our cities in highly industrialized world today by constantly pumping in artificial energy. And there's a concept called entropy pump. We're pumping in artificial energy in order for system not to come into thermodynamic equilibrium with its environment and collapse. And this is also very important. While in natural ecosystem, only very stable or mature ecosystems are considered to be the good sort of state, a stable state, and they have a lot of species in them, and everything is functioning very smoothly, but it needs very little. Of course, it uses solar energy as a source of energy, but within the system, most of the matter and energy cycles are closed. And this is very important because this is, in our minds, the concept of future sustainable city. So basically the city that has a lot of matter cycle closed, a lot of recycling going on, and it should need very little inflow of artificial energy in order to maintain its functioning. This sort of exists in some Danish industrial parks because this is their aim, to close the cycles and the loops and to minimize the inflow of artificial energy in substances. So, Hopkins and Svirejeva, in their book, formulated the fourth law of thermodynamics for ecosystem, that the aim function of living matter is to increase exergy. In other words, the ability to conduct useful work. And that evolution should mean exergy increase.